We study X24NQ. You can download this file, PDF file of this lecture notes from our digital library, kpop.org, and you'll find the table of contents. We are working on the X series. It's X24. X24 main textbook, the first law of thermodynamics, can be found by clicking X and lecture in Korean 이번 시간에는 and lecture in English. In this class can be found by clicking the button shown in the PDF file, and you can return to our digital library by clicking the button in the middle. If you still not subscribing this K-pop YouTube channel, then please click this to subscribe. Okay, so let's begin with the X24NQ. If you are good at physics, you can directly attack the problem set X24Q. All right. Consider a gas consisting of n molecules in thermal equilibrium at temperature T. The gas satisfies the ideal gas equation where P and V are the pressure and the volume of the gas, respectively. Identify the physical dimensions of the following quantities. What's that? This is the kinetic energy. Kinetic energy of a particle is 1/2 mv squared. Dimensions, its dimensions are energy and mass, velocity squared. And velocity is length divided by time. It's a square, length squared, time squared in the denominator. PV, pressure. We remember pressure multiplied by the area is a force. Or pressure is defined by the force divided by the area. So PV can be converted to PA times AL. So if we consider a box with the cross-sectional area A and width or height L, the volume is A times L. Therefore, PV can be expressed in terms of a PAL. And PA is a force, and force is mass times acceleration. Mass times acceleration, distance divided by time squared. And L here. Move this guy here, you'll find mass length squared divided by time squared. Oh, we find that they agree with each other. They agree with each other. Dimensions of the kinetic energy, dimensions of energy, and dimensions of PV. And force times distance. Aha, force times distance is work. So energy, work, they are of the same dimensions. So this one has the dimensions of an energy. N is the number that is dimensionless. As a result, if you are allowed to write this, then KBT must be of the dimensions of energy. Okay? Explain the first law of thermodynamics. First law of thermodynamics is nothing but the conservation of energy, including the mechanical work done by a gas and heat energy. The Q in the first law of thermodynamics represent the heat supplied by the environment to the system of gas. Therefore, if you accepted some input energy and if you spend some, then you save the remainder. This is conservation of energy. Input, output, you're saving. Okay? The work done by the gas is pressure times change in volume. Remember, the pressure multiplied by the cross-sectional area times displacement of the wall perpendicular to that area, then this one is the volume change of the gas. Remember, this is a positive if dV is positive. This is negative if dV is negative. dQ is positive if the system accepts heat. dQ is negative if the system loses heat. The internal energy change is closely related to the temperature. The temperature represents the heat energy contained as the internal energy of the system of gas. All right, remember, this one is positive if the volume increases. This one becomes negative if the volume decreases. What is a CV? C is heat capacity, but V, subscript V, represents a condition that the volume of the gas doesn't change at all. We used the first law of thermodynamics that represents the energy conservation and input as the heat and the output as the work done by the gas, and the remainder is saved as heat energy. In here, if the volume doesn't change, dV is identical to 0. Therefore, this one states that the system, the gas system does not work at all. As a result, the input energy coming from the environment in the form of heat is completely transferred to the internal energy of the gas. As a result, because internal energy is proportional to the temperature, because internal energy is total kinetic energy of molecules consisting the gas system. Therefore, it is proportional to the change in temperature, and overall coefficient is defined by the heat capacity at fixed temperature or constant temperature. The heat capacity of the gas at constant volume, not temperature, constant volume. Okay, so in general, this one can be expressed in terms of CVDT always. When dV equals 0, they are equal. When dV is non-zero, either positive or negative, then you replace this E internal energy with CVDT, but leaving PDV the same. So this is the general form represented by the heat capacity of the gas at constant volume. Okay? Explain the work done by a gas whose PV diagram is shown below. Okay, let's see. This is a cycle, and this is also cycle. And we have 2 plus the same except that the orientation of the path on the PV diagram are opposite to each other. Therefore, if I sum these two, this part and this part, they cancel exactly because functions integral from a to b and functions integral from b to a, their sum is exact 0. Okay, here we have the work done by the gas, then we replace this one with pressure and volume. Pressure and volume. Okay? All right. So they cancel, and this part also cancel. So if we sum these two, we have a 0. By the way, because of these relation, the work done by the gas from A to B, this is a positive. Sum the work done by the gas from B to A along the upper path, it is the same in magnitude but opposite in sign, so it is negative work. On the other hand, this part, the lower path from B to A is negative, and amount is this. A to B here is positive, that amount is this. As a result, this one is a positive and is subtracted by this. So area of this over region, this one is done by the gas. Here, positive. However, this part, they are the same in magnitude, but because of the orientation, negative, large negative, and small positive, the sum is negative. Okay. 5. Explain the thermodynamics of a free expansion. Free expansion expands the volume of gas from a certain size to a bigger size. By the way, the initial state, the partition was empty. This part of the partition was empty, and it is being filled by this part. During the expansion, there is no force hindering the expansion. So during the expansion, there is no force against the expansion, the system does not work at all. In addition, there is an assumption that there is no heat transfer. No heat is supplied, no heat is lost. Therefore, if I apply the first law of thermodynamics. I do not have dq, and I have the internal energy plus the dPdV. No work at all because no pressure against it. So this one is a 0. Therefore, 0 equals the d int plus 0. Oh, what's that? The temperature internal energy change is a 0 regardless of the size of expansion. So if I integrate over the path of this state, the internal energy change is 0. Internal energy is represented by temperature multiplied by something. Therefore, the temperature is invariant. The gas does not work at all. The gas does not accept or lose heat, and the temperature of the gas is invariant. That's it. Thank you.